This topic is going to cover piping optimization using Darwin Designer. If computers are so darn smart, why don't they just design the whole system for us? So this is a pretty tough problem to solve because there's a lot of things that go on with that. But the good news is Darwin Designer can help you do that design, provided you have some good design constraints. It's a lot like Darwin Calibrator in the context that it uses the genetic algorithms. But instead of solving for C and demands or valve status, it looks at the best combination of pipe sizes or rehab options given your constraints and your boundaries, your pressure or constraints that you've given it. So that's what we're going to find out what Darwin Designer does. So with Darwin Designer, again, you might think that optimal design would be easy. Just solve for the diameter instead of flow and pressure, but it's a really tough problem. It's the most highly researched topic in the water distribution research area. There have been hundreds of papers and dissertations on it. A lot of work has been done on this subject. Why is it so hard? Well, instead of solving a system of equations as you do with hydraulic or water quality analysis, you're solving a mix of equations and inequalities, which really kind of messes up the math. And there's some judgment involved in it too. Then you have some parameters that are like continuous variables, like flow, pressure, and some that are discrete variables. Have you ever tried to buy like a 17.48-inch pipe? Well, the design might call for that, but that doesn't exist. You remember back in calculus solving for global minima and having to distinguish that from a local minima? The solution space for this problem is full of local minima. It's really hard to specify either whether it's reliability or uncertainty within an optimization program. So whether or not a solution is more reliable or whether or not it's going to have lower velocity. You're trying to build a system that will not only work for everything in its own, but also predict the future perfectly. For one that will work even if there's a component failure. If something fails and a pipe's out, and your predictions could be a little off. So the goal is to not just to minimize the cost, but to come up with a reliable system at a reasonable cost, kind of a trade-off, if you will. And our solution in Darwin Designer uses the genetic algorithm to search for the set of possible solutions for the best one, or I should rather say, for the best ones. Again, we're not going to see one single solution that's going to be the best solution for everything, because one solution may benefit one area, one portion of the system, another solution may benefit another area. So that's where the judgment comes in. If you ask engineers and operators and managers about the real objectives for designing a system, you're going to get a lot of responses that vary all over the place. And first, they may say that they want the least cost, the cheapest thing. But then they run into the budget constraints and have to decide what design consists of that's going to have the trade-off between the objectives and the cost or budget that's available. Most research work has been done on the first part. Some folks like the second, the maximize benefit one. The third one is really what most people in the industry do, either explicitly or implicitly, doing this trade-off, corresponding to the three objectives here that we're going to see in Darwin Designer. In Darwin Designer, the first type is going to be called minimize cost, where you're really trying to find the solution that will meet your demands and pressure constraints, your design constraints, at the least cost. With the maximum benefit runs, you're going to try to maximize an indicator of system capacity without going over whatever budget you have. And I rather prefer the multi-objective trade-off one, because you aren't really having the computer come up with a single best solution, but rather multiple trade-off solutions. So as you increase the budget, you're able to have a better pressure benefit, and we're going to see that graphically as well. A nice little graph to compare different solutions. Okay, so there's two types of actions Darwin considers to meet the requirements. One would be a new pipe installation, and the other would be a rehab of existing pipes. For new pipes, what you're going to do is you're going to give the unit cost, the price per diameter, per inch diameter, per millimeter diameter. You're going to give the roughness and the material of the new pipe, the range of diameters to be considered, and whether or not the pipe is optional. So by optional, we're going to see in the workshop, you're going to see where you could actually put in a 0, and then that pipe would be optional. In some cases, a pipe paralleling an existing system could be optional, and you might not know if you need that one or not. You want Darwin Designer to come up with some solutions that include that or not. However, for others, a pipe may be installed to serve customers, and the only option is what size is that pipe going to be, because you need that pipe no matter what. It can't just not be there. To indicate that a pipe is optional, you'll use a 0 diameter included in the list of potential diameters. So that's your design constraints that you're giving it. Pick from this list of diameters, Darwin Designer. For the rehab options for the existing pipes, what you're going to do is you're going to specify the type of action being considered, whether you're cleaning, aligning, bursting, or slip lining, whatever it is for that rehab thing that you're going to be doing. And then you're going to specify the unit cost per diameter, and then whether or not you're going to consider to do rehab or not. So you could be putting in 0 inch diameter for that too. So kind of in a similar fashion, but instead of the cost of the pipe, you're actually going to be handling the cost functions for the rehab. And you put in also the post-rehab diameter and post-rehab roughness. That way Darwin Designer can actually look at, okay, if I use this pipe, it's going to have this new diameter and this new C value, and try and find the optimal solution that's, if you're doing a trade-off, that's cheaper, that's the cheapest for this set budget, then spend a little more. Here's the best solution for that amount of money. Okay, so Darwin is going to use the cost function, the price per foot or price per meter, and it's going to mainly use new pipes, so that the most important cost is the cost of the new pipe installed. You enter the cost function for the diameter, whichever ones you want to be considered, and Darwin also lets you consider the pipe rehab cost too, right? So it's going to be however much it costs per foot or per meter. And then you can specify different cost functions for different conditions. For example, in the central city, the costs will be much higher due to traffic and utilities, and everything's buried, and a lot more excavation and care that would have to be taken, as compared to another alternative where the pipes could be being laid out in the countryside, where paving costs and construction costs are considerably low. There's no traffic. It's a lot cheaper to install. So you can handle different pipe routes by giving it a different cost function. And again, now you're starting to get an idea of why Darwin Designer, why you can't just let the computer go off and design things on its own, because you know that it's going to cost a certain amount to go one path, whereas another path, less congested, would be cheaper. But then there's going to be some trade-offs. One of the trickiest parts of Darwin Designer, if used more than the least cost optimization, is quantifying the actual benefits. Darwin is going to try to provide the minimum amount of capacity to minimize the cost. You're going to need to specify how to determine the benefit. So as a surrogate to capacity, Darwin uses the excess pressure at key nodes as an indicator of the performance of the system. So again, it's going to look at how much more pressure it's delivering in excess and say, okay, this is a better solution because it provided an excess amount of pressure. For each design event, you're going to be able to specify which nodes to use in the evaluation benefit. They'll be unitized and dimensionless, and we'll show you a little bit more about that. So in the unitized, the benefit is given as the average pressure above the amount needed for the system to meet constraints. In the dimensionless benefit, the excess pressure is non-dimensionalized and weighted by the demand at the node. So in this case, the exponent B over here enables you to account for the fact that the first unit of pressure is worth a great deal, while the latter units are not worth as much. You can set a maximum pressure to account for the fact that you can have too much pressure. Maybe it's 190 psi or something. Set B to something less than 1, about maybe 0.5, to account for the diminishing return, where the greater the pressure over that amount, the less of a return it's going to be for you. When you look at trade-offs between benefits and costs, there may not be a clearly like the best solution. Instead, there's going to be trade-offs between benefits, higher flow, fire flow, better pressure, and cost. You spend more, you get something better, generally. In a trade-off analysis, Darwin calculates the benefit and the cost for each and every trial. So in this case, what we see on the screen is we've got 3 different potential solutions, A, B, and C. And take a moment to look at the screen and try and decide which of the 3 potential solutions would you toss out. If we spend a little bit more for design B, we spend more, but our benefit is the lowest of all 3. So that one tends to kind of look like the one that might not be as good as, say, C, where we spend less, but we still get a greater benefit than B. Then it comes down to whether or not A or C is the better one we might want to choose. It depends on what benefit are we going for, or how much money do we have to spend. So the answer here is the best solution would be A and C. It depends, but which one would we throw out? Probably B is the one we would throw out. Darwin looks at many thousands of solutions in a given run, just like the 3 that I showed you on the previous screen. But many of the solutions it looks at are inferior versus the ones that are non-inferior, the ones we are really interested in. Darwin discards all of those that are inferior and keeps the non-inferior solutions. So in this case, the red line on the graph here is representing the ones that we may want to implement. If money's really tight, you might go with a solution 6. If money is no object and you want the best benefit for what you got, hey, solution 1. But somewhere in between, solution 2, 5, it kind of depends on how much money you want to spend or the benefit you need. So this is really effectively what Darwin is heading towards with Darwin Designer. A design study, much like Darwin Calibrator, it's a study is where you enter in the lion's share of all the data and the information. You'll pick a representative scenario. You'll set up a design study event. You'll make any demand adjustments locally, set your pressure constraints, minimum maximum pressure constraints, any flow constraints, or any boundary conditions that are going to be unique to this design that you're trying to run. And you must test the trial solutions against at least one design event, something like a scenario, just to see if it's going to work. Just so and that'll let you know whether or not where you need to go with different data points, like to adjust your pressure constraints some more or something. So try and run a scenario just to see what's going to come up in the design. Then you can actually go to the study and put in your design constraints. Then set up design groups, which pipes you're going to be replacing, because you're probably not going to replace all pipes, right, unless you're designing a whole brand new system. So select the pipes that you're going to design, or if it's rehab, which groups of pipes you're going to rehab, and then again you'll need to enter in the cost functions for a new pipe cost function or rehab actions, and then select what design type. Is it minimum cost, maximum benefit, or trade-off? And in the workshop, you'll see you're going to go over all 3 of these, and then you run whichever design solution you like. You can then export that, promote that to an actual scenario to have and go run criticality on, run fire flow analysis. You have it to go play with as a scenario at that point. Okay, so the functions in the Darwin Designer Study, you can create, copy, you can do a lot in there, rename, delete. So if you really like a study but you're not quite sure if you really want to use this one design constraint, great, copy it, change it, and press compute again. Before you open Darwin Designer, you'll need to set up the representative scenario. Could be maximum day, if that's what you're trying to look at to assess the minimum pressures to make sure that they're being met. So set up the representative scenario. Then you're going to lay out the pipes to be designed. Any new pipe that's going to be sized in Designer needs to be in the scenario, needs to be active with active topology alternative. Any pipe that's going to be rehabbed needs to be in the scenario as well. And it's good to have a new pipe name or something like new, new-1, new-2. That way you don't get confused with a existing pipe network that's already there. It doesn't matter what size you make all of these new pipes. It could be 100-inch, because Darwin's going to come back in and figure that out based on the design constraints that you give it. For example, maybe another failsafe could be use 0.5-inch diameter. That way, in case you do have to run the model, it's really not going to impact the model because those 0.5 inch, they're not going to carry a lot, and you'll be able to see them fairly easily by doing annotation or color coding or something. Lay out any tanks and pumps and reservoirs that are going to need to be used. Definitely going to need to do that. And then also something to consider too, when you're laying out the pipes to be designed on step 2, what that really means is you are going to select the path, the potential locations that pipes are going to be. And this is another area where, a computer could go design a whole entire system, right? But it could be drawing a pipeline right through a building, right through a lake or a pond or something, or right through a sewer main. You, the modeler, would know about these things by seeing the overlay of the data and knowing that those are important elements that you can't put a pipeline through. So you actually need to guide Darwin Designer to say, here's some potential paths that you might want to consider. Like actually draw those out. Doesn't matter what diameter, again, you use, but the path needs to be there. Inside of the Darwin study, Darwin uses baseline demand for the demand alternative associated with the representative scenario. So whatever representative scenario, that's going to be the demands, the base demands. But you may want to enter in a demand multiplier and adjust that. Maybe you've got a pattern. You can specify that you want the demands associated with any given time rather than the baseline demand. So you can set that up to pick off a specific point in time. If you wanted to use the demand multiplier to adjust all the demands to some like peak hour, you can specify that in the study. If you have a different demand alternative that you have created in the design event, you can specify that alternative too. So you've got a lot of flexibility inside of Darwin Designer Study itself to throw some different tests at it, push it a little bit further to try and see what the design will come out to be before having to actually change and alter all of your scenarios and alternatives that you've already got set up outside of Darwin Designer. So it's kind of nice that it keeps everything kind of compartmentalized. If you have one node, maybe you'd like to adjust to correspond to fire flow, you can directly input that too. So there's, you can make specific elections of changes inside the Darwin study. Maybe it's demands for a hospital. You can put that particular flow that's needed or something there, or pressure. Okay, so let's see. So designs are tested against constraints to see if they are acceptable. You're going to set the constraints. This can be set up globally, the constraints on pressure and flow, or it can be set up by selection set or specific nodes. You can set pressure constraints to be like 20 psi globally, but then sometimes some of your nodes you may want to exclude. Like a node on the suction side of a pump may have a constraint of, say, 0 psi. So you could elect to put that for that particular node set. Maximum pressure, it's usually not a problem, but sometimes you may want to have this model indicate if it is. If you don't want maximum pressure to be considered, set it to be a high value. The default is going to be 200 psi. You also have the ability to set a maximum velocity, just in case you have some design criteria for transients or asbestos concrete pipe or something that you're trying to make sure you don't exceed a certain velocity in a design for a certain pipe set. And then node pressures included in the benefits. So again, whatever these are globally, or you can specify them individually within the study. So this is all done inside the study, not impacting your representative scenario itself. Okay, boundary conditions, same thing like we saw in Darwin Calibrator. You can make some local changes to your boundary conditions. So this is, in effect, temporarily altering the representative scenario to some level. Maybe you're going to see what happens if I use the lowest tank water level and a pump is off. Will this design scenario work out for me? What designs will Darwin Designer crank out based on that new boundary condition? So again, a lot of flexibility inside of the study to see whatever scenario, or I'm sorry, whatever design Darwin Designer can come up with in all the solutions. So you could override tank level, pump status, valve settings, pipe status, all that good stuff. Set up your design groups. Identify the pipes that you want to be candidates for the design. Group the pipes with common diameter, and what that might mean is, say, a pipe along a certain route. You probably want to group that together so it's not coming up and saying put in a 6-inch, then an 8-inch, then a 4-inch, then a 10-inch. That's not going to make a lot of sense. The contractor probably wouldn't lay it out that way. So group pipes along, say, certain stretches, and that's probably how it's going to consistently be laid out in a particular diameter. Plus, this also minimizes the time that Darwin Designer is going to have to run to come up with a solution, because you're grouping pipes and you're reducing the potential possible solutions considerably by grouping pipes. And set up logical group names, and basically in the example here what we're trying to prevent is 6, 12, 10, 8. That's probably not how it's going to be laid out in real life. So group those pipes together in northeast section NE or something. Just set up some grouping names. Like option groups, it might be a pretty silly name or something to have in the tab. But set up in the design your cost function, the new pipe roughness, the material. If it's a rehab, whatever the post diameter is going to be, the cost, that's going to go into your cost functions. And as with Darwin Calibrator, you have the option of using the optimization or manual runs. So those of you with WaterCAD, you could see this run in a manual way, but without the licensing in WaterGEMS, you wouldn't be able to run it in the automated fashion to come up with multiple solutions. With the WaterCAD side of it, you would be providing it, you would be selecting the diameters, and it would calculate the cost for you just for that selection that you manually made. But with Darwin, it provides you a real quick way to see all of the solutions. Maybe you actually want to run a quick manual process just to see ballpark for the costs of the pipes. You know, you're not quite sure. You know it's going to be a general range, so you just set everything to 10-inch. It could be 8 and 12s mixed up somewhere in there, but you just want to see what the general cost is. So that might be a reason you might want to run the manual version of Darwin Designer. So once you set up the design study, you can create a design run the design events, group the pipes together. If there's any rehab groups, there's some Darwin Designer options that we'll get into. But most of those are already optimized for you. Then you'll press compute. So what Darwin ends up giving you is a lot of information when it's done. You're primarily interested in like how big the pipes are, and you want to be able to compare the design constraints, how close all of the design constraints were met for each solution. And then ultimately what you're trying to do is find a solution that you really like, that makes a lot of sense, that you want to promote or export as a scenario, and then go run that design against a lot of other design tests like fire flow analysis, criticality, and the like. Maybe water quality or something, because you've got really large diameter pipelines in this design, and you want to make sure that that's not going to have an impact. Don't waste time with design events that don't control sizing. For example, like average day, minimum day, those aren't going to control size of pipes, and it's going to minimize the pipe diameters. That's not really what's realistic. So maximum day, peak hour, those are the ones where if you spend time in the design event testing those out, you'll see the pipe sizes impacted. You also see pressures decreased as well. So to get Darwin to consider reliability, you need to formulate the events that simulate like outages or breaks. If your projects are in different parts of the system, it may be better to break up the different design runs. That'll help Darwin run faster and not waste time sizing pipe in the south side of the town based on pressure in the north. That's where you would select the pipes that are going to be grouped to size for that design study. You may have to check the tank refill by forcing some inflow because maybe the controls might not be where you wanted them to be the worst case scenario. Some nodes you'll find cannot reach the minimum pressure, or will always be at some low pressure, and that again could be a pump suction node or something like that. So you can not include those in the design study. And one other tip, skeletizing the model helps you run faster, helps genetic algorithms run faster, but if you're really trying to size pipes in area, maybe skeletonizing, simplifying your model may not be what you want to do. Here's the procedure. You're going to construct the model, prepare your demands, get your cost data for the pipe diameters, come up with your alternative pipe plans, identify the pipes and routes, group some things together, identify your design constraints of pressure, set Darwin genetic algorithm optimization parameters, but again, you're not going to have to do too much in there, it's already optimized. Run the optimization, and then look at the results, tweak some things, go back in, copy the study, change some things, rerun it, and see if you get a little bit better design. What will your solutions look like? It's going to depend on the way you set up the design constraints and the objectives. For a simple system here, with 9 pipes in one tank, the least cost solution would look like this one, with minimally sized pipes and no loops. You can force looping by not allowing 0 diameter, and you'll end up with a loop system with small pipes. If you try to maximize the benefits at least cost, you're going to come up with big pipes with no loops. If you try to maximize reliability by including a lot of design events with outages, you'll get lots of looping and bigger pipes, but not as big as the capacity increase. In the end, you still need to be the modeler, the engineer, making the good decisions based on the solutions that are in front of you. Yes, Darwin comes up with and enumerates trials very quickly, but you still have to evaluate those solutions to make sure that they make sense and make sure that the design parameters were correct. Darwin's really smart in many ways, but it's really sort of an idiot or a savant like Rain Man. It calculates quickly, but it doesn't exercise judgment in doing so. Did it make sense to have that large of a pipe diameter in the part of the city where it's not really ever going to grow because there's no growth pattern out there for the next 30 years? You know that, the planners may know that, but your Darwin designer may not know the future of wherever that town, city, municipality is growing. Darwin highlights whatever level of assumptions you make because you make them explicitly. So basically, Darwin Designer makes design work easier.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.